time to start. So yesterday we discussed a little bit about dynamic programming principle, and I spent more than 1 hour and a half talking about this topic in the discrete case, because really this is the first step, and this is the first important step in the theory when you want to describe the value function, either by, so you can have already this dynamic programming principle, which is by itself a first characterization. And then we will go one step further and see that we can also describe in some cases the value function as solution of some PDEs, which makes a very nice link between the theory of optimization and optimal control problem and the PDE theory. But before that, yesterday we talked about some numerical difficulties and how to solve these equations. So today I will spend time describing some examples and also describing some algorithms, how we can solve this problem, what are the properties of these algorithms, okay? So this is the equation I will try to focus on today. So if you remember, yesterday we have something like 1 minus lambda v equal to a minimum of something c plus mv. And here we had some controls, u or alpha, and alpha belonging to a given set. Okay, so we had something like that. So I put it in a more general framework. This is almost a linear, so we are minimizing some linear systems, and what we ask is that the minimum is equal to 0. Actually here I will show some examples where we may end up with max mean. So we have two actions, the action of the first of alpha and the action of beta. Alpha is aimed to minimize this quantity, and beta aims to maximize it. So for the notation, I will consider that x is Rn, or it's something discrete, but with infinite number of components. And what I mean by, if two vectors are in X, what I mean by mean of f and g is the minimum component by component. So this is classical notation. And in everything I will say today, I will assume that these sets here, the sets of actions, are compact sets. So I will assume that these matrices here are known. So this matrix A is known, B is known, and the only unknown quantity is this vector x that solves the system. Okay? So I think I need to show some examples just to convince you that this is really related to what we are, the topic of these lectures. Some examples in optimal control problems. Then, the outline. Then I will speak about some non-smooth Newton methods. I will focus on a specific non-smooth Newton method called Howard's algorithm, and I will show you some theoretical results regarding this algorithm. So the first simple example is the obstacle problem. Okay, so the obstacle problem, you want to minimize. You want the minimum of these two quantities to be equal to 0. This is just q, x minus b, and x minus g. So the problem is very well known, and it's related to this minimization problem under these simple constraints. Okay, if a q is a symmetric matrix, then this system appears when you write the optimality condition of this simple minimization problem. And actually, this simple optimization problem is very important also in PDEs. For example, if you discretize this kind of equations, now here my u is a function of s between 0 and 1. This is the Laplacian, which means in this case just the second derivative. So if you are asking the minimum between minus the second derivative minus f and u minus g to be equal to 0, then when you discretize this equation, you end up with this obstacle problem. Okay? And why I choose this example, because we will see later that this is exactly what we get when we want, for example, to have a value for American options. Okay, so every single example I will show you will be studied again when we will talk about the optimal control problem in continuous time. Okay, so so if you solve the problem, what you want is you want to have not only the linear system, actually you want to solve the system as far as x is greater than g. Okay, so why then the max mean? The max mean is comes when you have, for example, two obstacles. What you are looking for example, in this minimization problem is not only x greater than g, but x greater than g and less than another function h. So what you want to compute, it's this blue line, which in some regions it solves just, the blue line is the max mean. It's the max mean problem. So the blue line is the max mean, and you have to stay under this obstacle h, which is in red, and above the obstacle g. So this is what we, one kind of problems that can be also that fall in what we are looking to today. So how this kind of obstacle problems are related to the original problem I show you. What is the link between this and this, for example? So the link is if you have, oh sorry, I changed them. Yeah, the link is that if you have this minimum qx minus b and x minus g equal to 0, then you can define a0 like q and b0 like b for this part, a1 like the identity, and b1 equal to g for this other part. And then what you are minimizing is, what you are solving is that the minimum of these two vectors should be equal to 0. Okay? So exactly the general framework I wrote at the beginning like that. And in this example, the set of actions is just a 0 or 1. Okay? So, and the same if we have this double obstacle problem. If we have the double obstacle problem, then we take A0, 0 like a Q, B0, 0 like B. This is the identity. This is G for the first obstacle. And this is the second obstacle. And we can write everything also in this form with beta between 0 and 1, and alpha, it's a 0 or 1. Okay.
A to the power of alpha is just like an indexing, right?
It's like an index. Yes, it's an action. Yeah, it's a, yeah. Here it's discrete. No, it's not a power.
You're choosing different matrices.
Just choosing different matrices, and the matrices, they depend on the action. The coefficients of the matrix depend on the action. Yeah, thank you for your question. I should have made this precise. It's not a power here. It's a matrix depending on alpha. or beta. Okay, and now the third example is what we discussed yesterday, and I think we extensively discussed this problem of stochastic path problems. We consider a discrete time, so we have a discrete set of states, xi, the same notation like yesterday. We assume that our set admissible policies, you remember the policies, they depend in time. So it's alpha, each component of alpha represents an action that we will use at a time t, and all these actions should be in a compact set, for example, U. So for this associated to this set xi, we have some transition probabilities depending on the action. Okay? So depending on the policy alpha, we have different probabilities, and P alpha, it's just the transition matrix. So now, also associated to this control alpha, we have some costs. This is the cost that allow us to move from xi to another point on the same set xi. Okay, so things, we have this kind of Markov chain, so we can go from one point to another with a certain probability, and at each time we have an action alpha 0 to act. And when we use this action, then we move to other points with some probabilities. And the cost is just the summation of all these quantities. So this is for sure at this time, if we are at the position I, then this is exactly what we would pay. And then depending, so we mix, so this is an expectation of what we have to pay at the stage t equal to 1. So it's a combination with these coefficients that are the transition probability, and so on. And then the final cost is the summation of all these contributions. For each t, we have a cost that we multiply by, this is the discounted factor, and then we count everything. This gives us a cost related to the policy alpha that we are using. And the optimal expected cost is the minimization over all the policies. Okay, so this is how we defined yesterday our optimal control problem, and we saw that we have this Bellman principle. So this is exactly like that, apart that now I'm using the notation P for the probability and not M. Okay. And this 1 plus lambda, it comes from this term. This is we took this discount factor in this form, but we will see in other examples that we can also have another way for the discounted factor. Okay. So this was my third example. But still, in this example, we have this form that we can write exactly as a minimization. Okay? But at the beginning, I told you that we are concerned by the problem where we may have a maximum and a minimum. So my fourth example will describe a situation where we end up by solving exactly something like that with max min. So this is a two-person game. So we consider that we have a player that is moving with this motion. Yk plus 1 is equal to yk plus square root 2 epsilon b vk. and we are starting from a given position Xi. So we assume that the player is starting in this Xi is in a convex set in R2 omega, and its boundary is T. So I denoted T because it will be a target for us. So the game is includes two players, two opponent players. It's not a cooperative game. The player one, who is the evader, he started from this position inside, and his aim is to reach the target, which is the boundary, as soon as possible. And the second player, this is the pursuer, and he's just trying to obstruct him or to stop him. So what they have in hands is, for the first player, he can choose the direction V. He can choose the direction of his motion. It should be something with norm equal to 1. The second player, he can just put a mirror. He can let him go in that direction, or put a mirror and put beta equal to minus 1. So he can change V with the BV. And each step of the game costs epsilon. Okay? So for example, if he started in this position here, so maybe he could be tempted to go in this way, because this is maybe the faster way to go to reach the target. But then if the second player choose B equal to minus 1, then he would find himself even farther from the target. So he has to play very well and very carefully to be sure that each V that he will choose, even minus B, is not far. So this is a smart idea to go in that way. So if the second player choose B equal to minus 1, then he would find himself here. Okay? And so if we have k steps to reach the target, then the value function would be k epsilon. Okay? But we don't know how many steps we have to do. So if we write the dynamic programming principle, we end up with this equation. Vxc is the minimum over all the vectors V with norm equal to 1, maximum over beta with value plus or minus 1. This is the cost for one step, and this is the value function next move. Okay? When you move from epsilon, you arrive here. But this is something, I should have put here, B, it's plus or minus 1. And
which player?
Sorry?
There are two players. This is the payoff for player 1?
Yeah, it's from the point of view of the player 1. So we are taking the point of view of the player 1 who wants to minimize. He wants to minimize over any action of the second player. Okay? And if we are already outside, then the value is equal to 0. So now, if we want to solve this equation, it's a nonlinear equation, and omega is a convex set. So we have to do some approximations. So we take a grid on omega, not necessarily with a uniform grid. It can be any grid. So we take a grid in omega, and let me call it again xi. Remember, n could be equal to plus infinity if you want, but here, since we have a finite, it's bounded omega, then we can have n is a finite number. And then the scheme is the following. We are just projecting the dynamic programming principle over this grid G. So we are asking this equation to hold for every xi. So VI stands for an approximation of a V of Xi. And as I told you yesterday, when you start from a position which is on the grid, you are not guaranteed that the next move would be still on the grid. So this is why we use here an interpolation of the same vector. Okay? If this new position is not on the grid, then we have just to interpolate the values. So, and by the interpolation can be, again, we know that it can be considered like transition probabilities, the coefficient for the interpolation, because if we have a monotone interpolation, bilinear, for example, linear approximation, then can be interpreted like a probability transition to, oh sorry, this should not be U, this is V. Sorry, and here again, it's V. Sorry about that. Now, if we sum up, this is what we get. We get again an equation with the mean max. V, it's V, and here also it's a V. I'm sorry. I will correct the slides before posting them on the website. So now what we are looking for is just a vector in Rn, and V is a solution of this nonlinear system. And by the way, this very simple game problem, two-player game problem, is related in physics to front propagation with mean curvature. So it's a nice link between PDEs. So I didn't show here the PDE, but the problem can be interpreted like a two-player game. Any question? Okay. So I still have two more examples. The fifth example is an infinite horizon control problem without stochastic. So we are minimizing this infinite horizon cost. And now I changed just a little bit, because I don't want you to be disturbed if I change the discounted cost. Of course, I will get something else for the dynamic programming, but the idea behind is still the same. Okay? So the same proof works. So here I take this kind of discounted factor. L is the distributed cost. And we assume that we have a dynamics in depending on the action of the control UG, starting from a position of X. And UG, as usual now, is supposed to belong in a capital U, which is a compact set. So the optimal value is the function is in this function V of X. So I assume that everything is Lipschitz continuous, and I assume that we have the minimum of the problem. So the dynamic programming principle in this case, it's slightly different from what we had here. And it's different just because I choose another discounted factor. So what we get is this form. But still, we have, because we are in the infinite horizon and our value function depends only on X, we have a formula that links V at the position X to the next position, which is Fxu. Okay? So this is the next position. So, again, if we want to have something that we can solve, we have to use some approximations, and here we consider again a grid G. Xi denotes the nodes of a G, and Xi they are considered now as part of a Markov chain. So an approximation of this dynamic programming principle on the grid G is given by this formula. Here you can recognize this is the value at Xi. This is what is supposed to be the value at Xi. This is an approximation. This is the distributed cost. And this is the function at the next move, next position. But again, since we are not sure that this is a grid point, then we have to interpolate. So the interpolation gives us some coefficients, lambda, that are between 0 and 1. The sum is equal to 1. And if I take the sum of lambda times Cj, then I end up with exactly this term. Okay? This is how we interpolate. So, no, sorry, for the moment I'm not yet interpolating. I'm just looking for barycentric coefficients on the grid. And there is always, if this is in if I don't know if it is in J or not, at least I'm sure that there are always some coefficients, positive coefficients with sum equal to 1, and F is given by this combination. Yes?
I think in this approximate dynamic programming, those lambda become variables of the in the recursion. Is it something that we can do in some cases?
Actually here, they depend on the control U. They depend on Ci, but if it doesn't...
First U and then you choose lambda, right?
Yes.
I think those approximate dynamic programming people, Warren Power and all those, they choose lambda together. It says it's part of the variables there. I don't know if it becomes nonlinear.
No, it's linear. But let me show you how it's... This is what it gives. Oh, my lambda are not a good choice. It's also the discounted factor, but... okay, it appears here. So yes, you have something now that is bilinear. Yeah. But I don't think you can... you can minimize over U, or you minimize over lambda imposing this constraint. You can consider your control problem in another formulation if you want. Yeah, you can do that. Okay, so this is now a linear. So for me, we compute first for each control U. You can compute this matrix MU. And then you end up just with this equation, and the lambda U, they don't have anything to do with this lambdas, okay? Different notations. Yeah, I choose to show you how it works first in the deterministic case, just to emphasize on the fact that this connection with Markov chain approximation is not related to the stochasticity of the problem. It's just because we are moving from one point to another. When you project on the grid, then you have this interpolation that can be interpreted as a probability, transition probability matrix. But it hasn't to do anything with the stochasticity of the control problem. So now if we have a stochastic control problem, I take almost the same kind of problem we have here. We are maximizing this time, an expectation. I just made a precise a little bit the model. So earlier I put it like F, and here I took an example of what is called in the literature irreversible investment models. So in this model you have a company, and what you are looking at is just the production. So what you can do at each time is to choose. So X is the generating capacity of the firm at time T. And you can at each time decide a number of capital units that you move from another business to this firm. Okay, this is U. This is the control you have. So when you move this capital units to this firm, it costs you beta UT. So you can bring more money from another business, for example, but it would cost this quantity, and the factor beta, we assume that it is known and it can be interpreted like a conversion factor from one business to another. So if you take money from one business, you put it in another business, it's not the same money anymore. And so this is how it works. If you add this U, then you increase your capacity. Delta is just the depreciation rate of production. And we have some stochasticity here. So WT is a random variable that can be plus or minus 1. Sigma is the volatility of the market. And WT is equal to 1 or minus 1. And to make it simple, I put a probability 1/2. But usually, it's more complicated than that. So the costs, we assume that we have a profit cost, C, which is utility function, concave and increasing function. So this is the control problem. And this should be also max, I'm sorry. This should be max. So if you write the dynamic programming principle, it gives you this, this form. So here again, the form of the discounted factor give us here this coefficient 1 minus lambda. This is the cost, the distributed cost, and this is the next move. If you start from x, then this is the next move. But in this next move, you have some randomness, lambda, and you take the expectation. But this is not a problem because we know that this omega is equal to 1 or minus 1 with probability 1/2. So the expectation is very easy. It's just this combination. I'm really sorry. I don't know why this minus. It's plus. We have a combination with 1/2 here. Okay. So you have to be careful with my slides. Stay awake. Okay. And then from here, you can use the centrics. I will not write everything again. You take a grid. You choose an interpolation, barycentric coefficients for these moves, and then you compute everything, and you have your transition matrices. So this is my last example where we have this kind of situations. So we saw more situations where we have the mean, or the max, but there are also a lot of situations where we have the max mean or the min max. Yes, please.
Is there a name in the literature for this technique of choosing barycentric coefficients and so on? Is that
Actually, there is maybe the book of Kouchner and Dupuis. Kouchner and Dupuis, from my point of view, is a very good reference to learn about this numerical aspects and to see the interpretation of numerical schemes as a Markov chain. Yeah. The book of Kouchner Dupuis definitely is a good reference for that. I can give you some lecture notes, but I think the best reference would be Kouchner and Dupuis. Okay. So now we come back to this equation. This is an optimization problem, right? But I hope I convinced you that this is one of the issues we are faced when we want to solve the optimal control problem by a dynamic programming principle. So what I will present next is a non-smooth Newton method to solve this kind of equations. And more generally, the Newton, or this is extensions of the known Newton methods. I don't need to remind you what it is. So if we have a non-smooth equations, and non-smooth, it means that f is So the min max is not a differentiable function, okay, right? But in some situations for non-smooth functions f, we can extend the Newton methods, and this topic have been extensively studied by many authors, because we have this kind of situation, as I told you, when you write the optimality conditions with the constraints, then you have this kind of equations to solve. So what does it mean, a semi-smooth function? So we take f, a locally Lipschitz function, and we say that it is semi-smooth at point x if you have if it is directionally differentiable and at x, and you have this formula. Okay, so this is not, since it is a Lipschitz, you have sub-differentials, but what you want here as m is an element of the sub-differential, and this quantity, we say that the function is semi-smooth if this quantity is equal to small o of h. So for example, if you are in these situations, even if your function is not differentiable, but you still have some directions that you can use to get this like Taylor-like expansion. So this is a very simple example of a smooth, semi-smooth function. And if you have a semi-smooth function, then the non-smooth Newton algorithms is in this form. You choose a regular first initial guess, x0, and you at k equal to 0, which is your you are starting the algorithm. At the iteration k, if fxk is equal to 0, it means that you have your solution, you stop the algorithm. And if not, you take a direction in mk, in the sub-differential, and you solve this equation. This is, you see, if my function was differentiable, I would put here the gradient to have the Newton method. But in the Newton method, we replace the gradient by an element in the sub-differential. And you continue your iterations. So you put k equal to k plus 1 and come back to 2, the step 2. Yeah, I said that we choose a regular x0 at the first step. And here this is a reminder what it means. It means that if x is a regular, if for any element in the subgradient is invertible. So 0 is not in the subgradient. And it is known in the literature, so I gave some names earlier, that if the function f is a semi-smooth function, and if your x star is a regular point, then you have a superlinear convergence. Okay, the superlinear convergence, it means that this quantity goes to 0 when k goes to 0. So this gives a convergence of the algorithm and also a rate of some rate of convergence. This is better than linear, but usually the Newton method is a quadratic, but here you lose something. You don't have, you have something between quadratic and linear.
That function is semi-smooth.
Because for the function, yeah, almost. I'm coming to that. Actually, this function, this kind of functions, if depending on the sets, if A and B have a finite number of elements, they are semi-smooth. If not, if you have compact sets, they are not semi-smooth. And this is why now I'm introducing another concept of differentiability. The concept of differentiability we are using here goes back to Kummer in '88, and it's called slantly differentiable. Slantly differentiable means that you have a family of mappings, G, such that you have this expansion. You see, G is not necessarily in the super differential. It's what you ask is just to have this family of mappings. G goes from your domain D to the space of linear operators between x to x. And if you are able to show that you have these mappings, then you can say that your function is slantly differentiable. So in the paper of Kummer, he gave some examples. Yes? Weakly semi-smooth? We can check. I don't know. Okay, so we can maybe check, but whatever. Kummer called it slantly differentiable in '88, and he shows some examples where you have this differentiability, but the function is not semi-smooth. Yeah, people sometimes they give different names, but whatever. I think the concept is this one, and you can find it in this paper, maybe in other references and their other names, as usual. Anyway, this slanting function, as I said, is not required to be an element of the super differential. And of course, if a function is semi-smooth, then any elements of the sub-differential would serve as a slanting function. Okay. And now this is another version of Newton algorithm, non-smooth Newton algorithm, but with slantly differentiable functions. So everything is as before. You start from a given point x0. You stop whenever fxk equal to 0. Otherwise, you keep improving xk by this formula, where here now what you use is your slant differential function. And it is known also since 10 years maybe now that the algorithm here is also convergent, and the convergence rate is super linear to the solution. And there's some assumptions. So the assumption is that f should be slantly differentiable in a neighborhood of the solution with the slanting function g. And you need also this g to be non-singular for any element in this neighborhood. And you need this boundedness. Well, technical requirements, but under these requirements we have the convergence, and we can prove also the superlinear rates. So these results, for example, can be found in a couple of papers by Ito and König or Ulbricht, the book of Ulbricht. Okay, so all this, yes, please. Yeah, of course. Yeah, this is what I have here, yes. This is like in Newton. You don't do better than Newton, okay? You're not supposed to do better than Newton. Even when Newton works and your function is differentiable, you have just a convergence in a given radius. So you should be close enough to start, to guarantee the convergence. Okay, so this is just some theoretical reminders about non-smooth Newton method and general requirements. Now, what can we do for this specific case where we know our matrices and our function f is not an unknown function? It's not that general. It's exactly in this form. How can we choose these slant functions. Are we in the non-smooth case? Are we in the slant differentiable case? This is what's the topic of this third part. But before, do you have any question or remark? Everything is okay so far? So first, I will present the algorithm when we have a just minimum. Forget the maximization, forget the second player for the moment. So this is the problem. We want now just to find this vector x in Rn such that the minimum of these quantities is equal to 0, A alpha and B alpha. I remind you that they are knowns. We know what are these matrices, what are these vectors, and we want just to find a single vector x such that this minimization is equal to 0. So before we go ahead, I would like just to remind you that since this minimization, I told you, the minimum of two vectors should be understood component by component. Okay? So actually, you can write it in another way where now you consider that you have policies. You have a control alpha, which is now a policy. So each alpha I is supposed to act on this row, the row I. Okay? So when I consider this minimization, I mean I'm not the minimization is of this vector is component by component, and at each row we may have a different value for alpha. I'm not trying to find a single value alpha for which this equation has a solution. I'm looking for a vector x such that the minimization component by component is equal to 0, which may require alpha to have different values. So the minimization can be reached for different values of alpha. For each row, we have a different value of alpha. Is this clear? So this is why it's a simple remark, but it's very important to keep in mind that this problem is not really minimization with respect to alpha. It's just solving this nonlinear system, looking for x such that at each step, if we minimize over alpha, it's equal to 0. But the minimum, maybe from one row to another, is not achieved with the same alpha. So now I look to this problem. It's not I changed just to the notation because now alpha is a policy. Okay? So we have different policies. For each line, I can choose a different alpha e. So it means that if I mix the rows, my system is still equivalent to the first one. Okay? Okay, this is very easy. The minimization, as I said, is component by component. So which is important is just to look at each step I, what we have, and you can convince yourself that what I'm saying is actually correct. And the Howard's algorithm is called also policy iteration methods, depending on the papers. It uses this fact, it relies on this equivalence form, okay? So you want, actually what you want is to find x such that the minimum is equal to 0. So if you have alpha, if you are given this optimal policy everywhere, then you would up just by a linear system, okay? And if I give you the solution, x bar, then here you can, from the solution x bar, you can get the optimal policy. Is this clear or not? So if instead of, okay, if you have a visor that gives you the optimal policy, then you are fine. You just plug this policy here and solve just the linear system. And also, if you are given the solution X, then to get this optimal policy, it means that you need just to minimize components by components, and then you get the optimal policy. So Howard's algorithm relies on this simple remark, and it suggests an algorithm on 2 steps. It's like a splitting method. So you have 2 operations, minimization and solving a system. So what you do here, you start by a policy now. You are given a policy everywhere, alpha 0, and at each iteration, you choose xk, which is a solution of this linear system for this given policy, alpha k. So you get xk, and now you improve your policy by looking at the optimal policy that minimizes this quantity with xk fixed. Okay? I call it a splitting method because you have 2 operations to do, and here you are iterating from, so in each iteration you have these 2 steps separately. You do these 2 steps separately. So it's not a new algorithm actually. It's you can find it in the papers of Bellman in the 50s, and then Howard gave first formulation of the algorithm. This is why it's named after him. Then there are some works in the 70s and also in 2004 giving some convergence results. And there are many other people. So Claudia also worked on this algorithm in '89 with Hoffman, I think. I found something. It's not called Howard algorithm, but it is. Okay. And actually, in all these results, you can find different kind of proofs. So which was really missing is this notion of weak differentiability, slant differentiability. So this is what we have, what you can prove correctly. So first you need some informations on the dependency of the matrices with respect to alpha. Okay? So what we need, for example, is either the set of actions is finite, and then you are fine. You have just a finite number of matrices, or this dependency should be continuous. Another important assumption that we need is monotonicity. But I know that recent results by people in stochastic control problem like Forsyth or Christoph Reisinger, they came up with some more general results with where they can weaken this assumption of monotonicity. But monotonicity is, you can have it every time. In all the examples I showed you, for example, our matrix, transition matrix was, it's a monotone matrix, for example. So this is not very restrictive in my point of view, and still I stress on the fact that you can weaken it. But anyhow, here I assume that it is monotone. Then what you can prove is that the sequence that you compute by Howard algorithm is actually an increasing sequence that converges to the solution. And if A is infinite, then you have the super linear convergence. And also, if A is finite, and since your sequence is increasing, then you have a finite number of iterations to perform. Yes?
So this original reference that you mentioned, they never proved anything like that. They just postulated it.
They prove something like that by adding more assumptions.
Oh, okay.
No. In this paper, for example, they prove even that there is a quadratic convergence. Okay? But quadratic convergence, of course, you can guess it. You need really much more assumptions to get the quadratic. I will talk about that later. Okay? So, the obstacle problem, for example, here it means that this matrix Q, it's monotone. For example, yes, okay? And if you consider that Q is the matrix you get when you discretize this equation with Laplacian, it is monotone, for example, okay? It would be monotone for any monotone scheme. Yeah, some people who don't like the monotone schemes, of course, but I think it's not an issue. I can put maybe on the slide more references. I mentioned Forsyth and Christophe Ressinger.
Monotonicity makes the sequence monotone sequence.
Yeah, this is important here. Okay. But the thing is that you can get it even for other
some subsequence.
For some subsequences. Okay, so just an idea of the proof to convince you that it's very easy. So very easy because, okay, so remember when you are given a vector xk, you choose alpha k plus 1 that's minimize this quantity. Okay? By definition of alpha k plus 1, you have this equality. This is xk. For xk fixed, you minimize to get a new policy alpha k plus 1, which minimize this, this quantity for a fixed xk. And since this minimum is, of course, it's better than just choosing the former policy alpha k. By definition. But when we with the policy alpha k, xk was the solution to the linear system. Okay? Now, then this is equal to 0, and this is also the case if you fix the policy k plus 1, xk plus 1 is the solution of this linear system. So what you have as a conclusion is that A alpha k plus 1 xk plus 1 is greater than A alpha k plus 1 xk. Okay, and since the matrices are monotone, then you get this information. This is just to show that the sequence is increasing. Now, by using same arguments, you pass to the limit and prove that you have a unique solution actually for your system. And there, the monotonicity, this kind of problem has a unique solution. You can prove that it is also bounded, just the fact that alpha k takes values in a compact set, you have continuous functions, then everything here is bounded. And when you pass to the limit in this equation, so if you consider that f xk is this formula, then by passing to the limits, actually, you prove that you have your solution. Okay, so this is very easy, very simple arguments to prove that the sequence is increasing, unique solution to the system, boundedness of the sequence, and you can prove also that what you get at the limit is really the solution of your nonlinear equation. So just in many cases, for numerical purposes in stochastic optimal control problems, we prove the existence of, for example, of a solution by using this kind of algorithms, Howard algorithms, for example. Okay. Okay. So now the link with Newton algorithm is it comes from here. F is this minimization. So as I said, we have two steps in the algorithm: policy improvement, policy evaluation. Now let us play with these two steps. And you can see that you can xk plus 1, you can write it in this form. Okay? So if if you play with these two steps in the algorithm, you can show very easily that you have this formula. And of course, this formula, it's like a Newton method, and you can guess that now your the differential function, it's or sub-differential or slant differential should be this one. So, so far we didn't really need the fact that it is a Newton method because, or a non-smooth Newton method, because you can prove the convergence just by simple arguments if you have the monotonicity. And the link with the Newton method actually would help us to get the super linear convergence. And so we need here some steps to study this, for example, the control alpha, such that A alpha x minus B alpha is equal to F, which means that you have here alpha, the arg minimum. If you fix x, alpha should be the arg mean here. Actually, what was done in the first, you mentioned what was, you were asking about what has been done in the original literature. People, they would here ask that this set is a single alpha. It's everywhere you have just one alpha that's minimizer, a unique minimizer. And they put some additional assumptions on this minimizer. So, so that this function becomes smooth enough. Without these additional assumptions, the only thing you have is that it is upper semi-continuous. And you can prove also that this function f is actually slantly differentiable. And this is the slanting function. So I don't think it is a non-smooth really function if the set of actions is compact, but you can easily prove that it is slantly differentiable, and this is the slanting function, with the alpha x here should be an element in this set. So now with this information on f, these results that you can prove on f just by the monotonicity of the matrices A, you can prove that Howard's algorithm is a non-smooth Newton method for a slantly differentiable function f, and then you get the superlinear convergence by the general theory. Okay? So the rates of convergence is very important. When you do numerics, it's very important to know what kind of convergence you can expect. And here you can expect the superlinear. No more unless you have more information and more regularity on this on this set, which is the set of actions minimizing f. Okay, so now that we know that it converges, let us look at some examples and see how it works. So the first example is Merton's portfolio problem. I'm preparing the future, the coming lectures. Merton's portfolio problem is also a classical problem in stochastic control problems. So what we are looking here is at the value function v, the value function which is the value of a portfolio. Okay? So it is known in the literature. You can find the optimal control problem or the equivalent form, which is the PDE describing this value function. So as I said, I'm preparing the future, and the aim of the coming talks would be to make the link with the optimal control problems and this kind of PDEs. So this is what we have. We have the value function v depend on t and on x. No, actually it depends on t and s. S is my asset, and the time t is running between 0 and capital T. S is the wealth of the portfolio. So sigma is the volatility, and alpha is the control. So we are investing some monies and playing with these actions alpha, and the value function, if you from the dynamic programming principle, and we will see that later, you can prove that it's a solution of this kind of equation. So here inside this minimization, you have something like a parabolic equation. So this is the derivative with respect to time. This is the second derivative with respect to space. This is the drift times the first derivative with respect to space. Okay? So the drift, usually we will see it later, is just the deterministic parts of the dynamics. And here this is the stochastic part with, as I said earlier, sigma is the volatility. So mu and r are just some coefficients. We will come back to the other formulation of Merton's portfolio problem, and we will see the interpretation of all these variables. So here what we need, S is the space, T is time, alpha is the control, is the action of the control, and we want the minimum at each time, at each position S, we want the minimum over alpha to be equal to 0. So at each time and at each S, we have a different value of alpha that makes this quantity equal to 0. And this is an initial condition at time t equal to 0. So usually this initial condition is just the payoff. So if you assume that, for example, that this payoff has this form, so not far from a utility function, then you can easily prove also that your function has this mixed boundary condition. So this boundary condition comes just from the fact that if you write phi prime over phi, this gives you p xp minus 1 this is SP, and you get P over S. So what you can prove is that your solution, or you can just use it as an approximation, you can V of X over V of, TS. So you impose this kind of boundary condition when you are at S equal to S max, and this is enough to solve the PDE. Okay, how can we solve this? We have to approximate. So far we have just seen when you have a discrete dynamic programming principle, and here you can have a taste what we get in the continuous time. So what you have in the continuous time, you can go to the PDE, and then at a certain point you have still to use some discretization, and when you discretize, again you have this kind of problems that appear here. So for the discretization now, we discretize the derivative with respect to time just by a finite, something like Euler scheme. The second derivative can be approximated in this way. This is a classical approximation for the second derivative. So in this notation, here this exponent represents the time, and here it represents the position Sj. Okay, so we assume that we have agreed on this. Remember, our space now is between 0 and S max. Between 0 and S max, we can have some nodes. We have also some discrete times. Delta t is just the step, the time step size. H is the space mesh size. And we replace the derivative with respect to time, the second derivative with respect to space, and this was the first derivative with respect to space. Okay? We had also an information at time t equal to 0. So this is given, this information. And we can add also the boundary condition. In the boundary condition, it's a mix between the derivative and the function v, and this is what we have here. So the derivative with respect to space is represented by this finite difference. And this is very classical numerical approximations for the PDE. The most important thing for us, okay, you can choose other stuff here. You can use different approximation. So the most important thing is that if you want accurate approximation, it's better to choose an implicit scheme, which means that at time n+1, I'm computing everything with n+1. You can choose the explicit scheme if you want, and then everything becomes explicit and you don't need to solve any nonlinear system. But this is really this would be really a bad idea for this Mertens problem, and it's known in the literature. So it's better to solve it with the implicit scheme, which means that we have to solve this nonlinear equation for each time step. So just to check that we are in the framework where we know that the algorithm is well convergent. So you can check the matrices. Everything is explicit. I take also this occasion, actually. I know that we didn't speak about the PDEs, but I take this occasion also to convince you that even with the complicated framework of PDE, everything, all these matrices can be made explicit. You can compute them. Okay? So you start from this equation, you discretize by this implicit Euler scheme, and then you look at your matrices. And what you get is you can check by hand that the matrix is A alpha, So this system can be put in this framework with A alpha equal to identity plus delta t. Delta t, I remind you, this is the time step B alpha. B alpha is the matrix where the coefficients are given like that. So everything that the coefficients are explicit. So you can implement the algorithm here. So we have also the coefficients B can be made precise, and actually B is just a Vn. So at each time step here, you know Vn, and you compute Vn plus 1 by solving this nonlinear equation. And you can check that this matrix here is monotone, and there are some conditions, which the condition called in the literature CFL, condition Courant-Friedrich-Levy, which is a condition linking the time step with the space step. Okay, all these things comes, you open a book of numerical analysis of PDEs and you can find this stuff. Yes?
Well, the Newton method that you use at each iteration, you can probably use the solution of the previous iteration to one structure.
She's very smart. Yeah, this is what we will do. And actually, yes, and there is even in some cases, I will show it later. This is exactly, it's not just an option to, yeah, I will explain. Yes. You know that Vn plus 1 will be close to Vn. Then you have you can use it as a first guess because you know that you are close enough. Okay. So just the result, I will come back to. This is just to show you we have a situation where we have an exact solution. So this is why I chose this utility function, because Mertens portfolio problem has been studied for many payoff functions, and one of them is this utility function. And we know the exact solution. So we draw here on black the exact solution, and in blue you can see that Howard is just doing fine. And you can also get the optimal policy. So this is the optimal policy we get, but it's not really exactly what we were expecting. So the exact solution tells you that the optimal policy is a fixed policy, okay? While here we have something that started here and then goes up and reaches the level. So we have convergence of the value function. We have a quite good approximation of the policy, but there is no convergence of the policy. And this is very important to notice because I presented many the theoretical results, all saying that you go to, so remember here we have 2 steps in the algorithm. I get lost. We have 2 steps, the policy improvement and the policy evaluation. So when we improve this policy, we fix xk and we change the policy itself. And then we have this, when we have the policy, then we solve the linear system and get the solution xk. So which converges is only x, not alpha. Okay? That would be really interesting to find something that's help us to prove the convergence of the policies, but we don't. And you can see it in this example. It's not too bad, but still it's not perfect. It's far from being perfect. Yeah, coming back to some previous works in the literature. So this is situation, for example, if you have this kind of situation where you have quadratic functions with respect to alpha. Then you can prove that you have a unique minimizer. And then here you can prove a quadratic convergence result. Okay? So it's a very specific situations where you can really prove here that you have a unique minimizer of the function alpha and minimizer here. And then here you can prove that you have, so not only you have a unique minimizer, but you have also some Lipschitz regularity result for the function B. So I don't want to go more in the details, but you can find, if you are interested in situations where you can get quadratic conversions, just be prepared that you need really the minimizer to be unique, you need more regularity, and you can check in this paper what are the exact requirements. I think is it possible to make a break now?
You are the boss.
Okay, so I suggest that we make a break now. I start to get tired. And then after the break, we can come back for the second half of the talk. Okay? Tomorrow, we have a lab at 9. I had in mind tomorrow, if it is possible. I had in mind to schedule a lab for today, but I think it's better for people who don't want to attend the lab, just they can skip tomorrow. You are free.
To change the time then.
Okay, yes.
And on Friday we will use it?
And no, a Friday I will be just
Okay.
two
So,
lectures.
something that also I want everybody